Welcome back. So, we stopped our previous lecture by looking at a general block diagram of the hybrid force motion control law design based on feedback linearization. We mentioned that this is performed in a special space, which we have called task space, associated to a task frame. And we have used the parameterization of the free motion direction using scalars S and of the contact wrenches using scalars lambda. We have seen also that we need to make a filtering of measures from the actual measurement from sensor that we have on the robot, so encoder position and implicitly velocity, and the effector force and torque from the force torque sensor mounted at the final flange. This general scheme applies to any type of hybrid control. We have also concluded that it covers also limit cases when we have only motion control or only generalized force control. Now, there are cases which are simpler and in which we can use a simplified version of this scheme. In fact, this was the original version proposed by several authors, and then we modified it to make it more consistent. So you can see in this slide that there are only natural quantities, no S, no lambda, nothing like this, because in fact the single component of the generalized force, which we denote here as capital F, so with a linear force F and torques M, and of the generalized velocity, which contains the linear velocity and the angular velocity, the single components of this vector can be used, in fact, for parameterizing the task. Accordingly, the two matrices Y and T are in fact only selected columns of the 6x6 matrix, identity matrix. So it will be a selection matrix made by zeros and 1. This is also what you find in the textbook, in fact. So let's comment here. The principle is exactly the same. So we are doing a feedback linearization in the task space. But let's start first with reminding where are the quantities measured and then compared. For instance, we have on the robot side, we have a force measure, so in a sensor, force torque sensor in the frame of the sensor, typically mounted on the end effector, and we have some sensor kinematics. The block is intended to make the transformation of this measured force into a force defined in the base frame, so in a common frame. Similarly, the robot kinematics in the block below the robot block at the end of the diagram includes the differential kinematics. So from measurement of the Q and Q dot, we will compute through the differential kinematics also the generalized velocity, and this is typically expressed in the base frame. So Fc and V are both defined in the same frame. Now the R matrix, which is present on both channels, will transform this quantity into the task frame that we define as RFT, so reference frame task. Now after that we select the component, and this selection is done by two matrices, sigma on top and I minus sigma on top, which are in fact the selection matrix with zeros and 1 in their columns. So in the force loop, we will select only the admissible reaction forces that we are evaluating. In fact, there could be extra component in the Fc vector which are simply neglected. No? So those that are not consistent with the model of the interaction task. These forces are compared with the desired forces in the task space. You generate an error, and you have a controller that generates the force control loops. those that we labeled in general with lambda. Now lambda is not needed because we can use components, as I said, of F or M as a parameterization of these reaction forces. In much the same way, and complementary to the previous loop, we have the velocity loop. So we rotate the velocity in the task frame by the same matrix R. We select complementary, so where there's a 1, there's a 0, and vice versa, from the diagonal matrix identity. And those are the velocities that are feasible, so those that are comply, or better say, that are not barred from the presence of the environment, so the free motion direction. Again, we compare with the reference value, we generate an error, we have the velocity controller, for instance, a PD version of this, in fact velocity, but this can include also an integral term and be the position control with a PD in that case. The two commands are complementary, so they are integrated because each component of AF and AV act on a different direction of the task space. So we build the full, in general, 6-dimensional vector A, and this task acceleration through kinematic transformation, which involves the passage back from the task to the Cartesian, from the Cartesian to the joint space, and then we get an acceleration Q double dot plugged into the dynamic model. We have the nonlinear feedback innovation control in this block that generates the torque. So we have exactly the same scheme as before, but now without introducing the extra term, because these are simple tasks. Okay, there are other possible modifications. One that is quite interesting for me is the fact that despite we assume that there are, in the nominal case, directions that are constrained by a stiff environment. So in that direction we cannot have velocities, we can only control forces. There are situations in practice, and this is why this formalism applies also to the non-linear ideal case, where the contact in those force-controlled directions is in fact with limited stiffness. So there's no rigid contact, but a finite stiffness, namely a compliance, that can be used for designing still a force control in that direction. So the task frame is actually, in this context, only a selection of direction where to control force and where to control motion. In the force control direction, you can assume that everything is rigid and apply the method that we have seen before. So after feedback linearization and decoupling, you close a feed forward of desired force plus an integral term of the error. However, you can design a force controller in that direction, mimicking a behavior of an impedance model. And let's see how this is done. In fact, this is what we have implemented originally in our experimental setup, and I will show immediately some videos of what we have done. So within a hybrid force motion framework, the force control direction are we design a force control loop in the force control direction using a special impedance model. So let's consider that this direction is one axis, and let x be the position of the robot and effector along such a direction. X desired will be the contact point, so we count displacement from this position where there's a pure contact when x equal to xt. The contact will have a finite stiffness. Now we have seen that if we model with a spring the interaction between robot and environment, a single spring may cover essentially three cases. When the robot as a whole is stiff and the environment is compliance, or when the environment is stiff and the robot has some compliance, typically at the force torque sensor mounted on the end effector. We know that some deformation should occur within the sensor in order to be able to measure force at all, or when we have both situations, and what is in between the two springs modeling the sensor stiffness and the environment stiffness is in fact a negligible mass. Then we have seen that there's an equivalent single spring stiffness that we can consider in place of the series. So typically here we assume that, for instance, Ks is the sensor stiffness or whatever we have in that direction, and we know usually the sensor stiffness, so this is more convenient. Otherwise, we have to estimate something here. And Fd will be the desired contact force in that direction. This is completely different from the impedance model, where we do not regulate the contact force, but essentially we keep them limited by suitable choice of the parameters in the impedance model. Now, in this case, we choose as impedance model in that direction the following one. So an apparent mass, or inertia if you wish, M, with some desired damping dm. M stands for model in this case. And now the third term, the stiffness, however, is not of free choice. Is in fact Ks times x minus xd, which is nothing else than the measurement by the force sensor, if Ks can be taken as the force sensor stiffness, so the most compliant element in the contact. So only the apparent inertia and the apparent damping can be chosen as free parameters in this impedance model. On the right-hand side, we see that we would like to react to the desired contact force. Typically, Fd is constant, but not necessary. So if this is the model, and if we have applied feedback linearization before, so we reached a situation where in the direction x we have a double integrator behavior, so x double dot equal a of x. Now with this special, simplified impedance model at hand, we generate the command so as to impose that model to the acceleration. So the a of x, the input command on the linear side of the problem, will simply be 1 over the apparent mass. If you bring Ks x minus xd to the other side, and remember that this is the sensed force, you will create a force error, Fd minus Fs, and you will bring also on the other side the damping. So what results is that what you're doing in that direction is a p regulator, so proportional to the force error, so a p regulator of the desired force, and you have a velocity damping, so without the need of any differentiation of the force measurement, which is always a bad choice, in fact. So this is very nice, also because you can apply this even before getting in contact. So the same control law, without requiring any switches, can be adopted before the contact, while approaching the surface. So in that case, the measured force is 0, and you can, by the choice of positive gains, so M and dm in particular, in the impedance model, you can recognize that you start from rest, you get a force in that direction Fd, and this will let the system start to move, but because of the damping dm, you will reach a steady state speed. And this steady state speed can be computed by zeroing the acceleration x double dot, or the a of x, which is equivalent in that formula, which gives that the steady state speed at which you will approach after some initial transient the surface will be proportional to the desired force, but you can reduce it by a suitable damping value dm large enough. At some point you will get in contact, and without changing the control law, you will regulate force. So this is a very nice behavior, which is typical of the impedance model scheme that does not need to change its structure while transiting from free space to contact space. But here you can use this feature also within an explicit regulation of the force. I think that this is very nice, and in fact this is what we originally implemented in one of the first, I would say, worldwide experiment on hybrid control, including the full dynamics of the robot and realizing feedback linearization. So at that time, and you can see that it's many, many years ago, maybe a bit embarrassing, but you should not consider this as a limitation. We received in donation from the research center of the Fiat, now FCA, from Torino, so which had a section which is the ancestor of the current Comau company producing robot and automation system worldwide. We received in donation this prototype, which was called MIMO. I think that the acronym stands for multi-operation manipulator, something like this, completely naked. So this was a 6 degree of freedom robot with harmonic drive. So I will describe it in the first video, which is essentially describing the setup and then a few initial experiments. Then the second video will describe exactly the hybrid force velocity controllers. So naked means that it had no software at all. It has the power electronics for driving the motors. We equipped it with a Hungarian force torque sensor. So let's see how this worked at that time. So this is the force torque sensor. It's a very efficient one. We mounted a rubber nose, and we will see why this. And this is the full structure. It's the view. It's very homemade. So it's a 6-arm manipulator with a spherical wrist, DC motors with harmonic drives, and a set of springs which are not seen from this side. They are beyond, which compensate gravity. Now the force sensor was a 6-dimensional force torque sensor with 1 kilohertz of data rate, which was very, very an excellent performance at that time. It became standard in 80 product 10 years later. Now, the first experiment is force control. So we regulate force. If we push before the force torque sensor, the force torque sensor is not sensing any force. The reference for the force is 0, so the robot stays at the same place. But if we push and pull the nose, the motion will follow. So this is a kind of a joystick for the robot. As the sensor senses forces, the motion will command in the direction of the sensed force, so the joint will move accordingly until the force is being reduced. Of course, if you continue to push and pull, the robot will follow you. Now, this type of behavior has a problem because the velocity that you realize as a reaction to the sensed force at the Cartesian level should be implemented with joint command. Now, if you invert velocity, you encounter singularity of the Jacobian. So we implemented at that time a robust singularity robustness scheme, so a damped V square. And you see that if you're bringing the robot close to a singularity with the second and third link being stretched, there could be very large velocity being generated, but these are in fact damped. So by pulling and pushing and effector and sensing forces, still you see that there is some acceleration close to the stretch configuration, but nothing too dangerous. So this was preliminary to what we've done, and in the third experiment, the last in this video segment, we are approaching exactly with the control that I showed before. In the approaching phase, we have a constant speed regulated by the parameter of damping along that direction, and then we contact and we apply, in this case I think it was 20 Newton. Now, to understand how old this video is, you may see now some VCR screen from the IBM XT computer that we were using for programming the controller, and you see that the force had been regulated to 20 Newton after initial transient approach. Now, the second video deals with more experiment, or 4 experiments. The first one is really a hybrid task. So the robot gets in contact with the environment, touching it with its rubber nose, and then moving straight along a straight line. This is another view. We put some choke at that time in order to understand what was going on, and at the motion was a trapezoidal profile with a peak of 0.1 meter per second, and we switch from 0 to 20 to 40 Newton in the normal direction, as you have just seen in the VCR plot. And this noisy signal is just around 10 to the minus 4, which are the position error along the tangent and along the normal on the plane. The second experiment, so the fifth in a row, we increase the maximum speed, so you will see a faster motion of almost half a meter per second. And again, here at the mid of the trajectory, we change the reference force along the normal from 20 to 40 Newton meters. And here you can see the trace. You can realize that the trace of the choke, of the rubber on the choke, enlarges when the force is being regulated from 20 to 40 Newton meters. So you push more on the surface, and the rubber finger will enlarge. You see here the variation from 20 to 40 Newton in the normal force to the surface, and again along the tangential direction of the straight line and the normal to the straight line on the plane, the position error is limited to 10 to the minus 3, so let's say 10 to the minus 2 or 3, so less than around millimeters. Now let me stop here because this is important. I would like to come back to this. Now the sixth experiment is in fact a step disturbance. So we assume that the table was flat, horizontal, but in fact we included a step disturbance. So at some point, while moving and regulating forces, there's a jump. And in fact, this shows the transient by the chosen parameter, and the normal force, having been regulated to 40 Newton, has a sudden decrease to 0 and then recovers. And you have seen the other parameters are exactly the same. So tangential velocity and normal velocity in the plane are not affected, they remain with very small error. And this is a ramp disturbance. Now we are ramping up, so the orientation of the surface is changing, but contact is still guaranteed, although in that phase, because we are not recognizing any change of orientation, you see that the force has a peak and then returns to the desired value. Now, if we, all the other quantities are exactly the same, so, and this is the final hello by the robot. Now, there's one consideration to be made here. These are the reference papers that you can access very easily in Explore. So the main issue here is, indeed, when there's a jump in the environment, or if there's a variation of orientation, the filtering effect of the hybrid force velocity control just neglect the components which are measured, in fact, by the force sensor, which are not only normal to the surface. I mean, they are normal to the surface, but not to the expected one. So those components are just filtered out, as well as the component due to the friction at the contact, which is large, because you have a rubber finger on a plastic table, let's say. So there will be some friction while moving, especially when we're pressing on the surface. So the tangent component of force, which is measured by the force torque sensor, is just discarded. So we are regulating just the normal force, because on the plane, on the tangential motion to the path of the plane, this extra force opposes motion, but is seen as a disturbance to be rejected by the controller. So the fact that we achieve still the desired velocity and we follow the position of our trajectory on the plane, despite the presence of this extra force, is thanks to the controller in the motion direction that reject this force disturbance. And of course, something similar happens in the complementary direction. Okay, indeed, however, and we will see that this information can be used to make things better. So to estimate online the fact that the orientation of the surface has changed and possibly also continuously. So let's see at this point what happens in the real world. So what are the sources of inconsistency when we get force and velocity measurement from the robot and from its force torque sensor, and they are different from what we expect the model to be, the interaction model to be. So the first cause of this inconsistency is the presence of friction at the contact, like in the previous cases. So typically we see in the free motion direction, which is tangent to the plane in the previous experiment, we measure a force that comes from the interaction, so it's a reaction force that opposes motion in general, although there should be none if the environment was perfectly a geometric one, zero friction at the contact, geometric orientation correct. By the way, there's another coupling effect here, because in case of a certain form of friction, like Coulomb friction, the force that opposes motion along the tangent, so on the plane, its intensity increases with the applied normal force. So these two components should be, in fact, decoupled. There should be no force on the plane, and only force reacting from the environment along the normal to the plane. Okay. In this case, this phenomena couples that the more we apply force normally, despite the nominal decoupling, in fact, there's a coupling because of this unmodeled effect of friction, and the coupling increases. So in the direction where we control motion, we will see larger disturbances that we have to neglect. So this is a first effect. The second effect is the presence of compliance. No? We assume that everything is rigid. Then we have seen that we can adapt the hybrid force-velocity, force-motion control scheme to the presence of some compliance in the contact, essentially at least the one related to the stiffness of the sensor, which is finite, and then we can design a force control loop using the impedance paradigm in that direction. However, the compliance in the structure may be at the contact, as we see, for instance, in the sensor, or, for instance, in the nose. Let me call this rubber object the nose of the robot, which is indeed compliant, so the contact will, position of the contact will be not uniquely defined, but there's also other compliances, as we have seen in the scheme for force control, that comes from the robot structure itself, for instance, the transmission of the joints, the joint transmission that introduce some compliance, which means that if we measure encoder position at the motor, and we have, for instance, transmission compliance, and we compute with this motor position and their numerical derivative the velocity at the end effector, so beyond the compliant transmission, then we may compute or obtain velocities in some direction that are nominally constrained. So it's like saying, oh, I'm penetrating the surface according to my measurement. Okay, so there's a mismatch of this. So you may have velocities where you don't expect to have because of the constraining environment. And this is caused by the compliance and the full chain that you're considering. Now, if, however, the geometry of the contact is perfectly known, then the fact that we are getting forces measured along direction where we don't expect them, or we are getting measured velocities or computed velocity based on measurement along direction where we don't expect to have velocities, this is automatically, these inconsistencies are automatically handled by the filtering of the pseudo-inversion with the matrices of the matrices T and Y, which generates the actual parameter S and S dot and lambda that are used for the control law. So this is being recovered. We avoid, as I said at the beginning of this lecture, we avoid, with the hybrid force motion control scheme, we avoid to become inconsistency in the control because of the fact that we are measuring things that are not consistent with our model. Of course, everything works if these inconsistencies are relatively small, so they can be treated as mild disturbances. If I'm 90% off in understanding the orientation of my wall on which I have to contact, then things may become a disaster, and we have to implement some adaptive scheme or some online estimation. And in fact, here comes the last point, uncertainty on the environment geometry. The first experiment that we performed were on flat surfaces. You will see at the end of this lecture other such experiments made at the University of Naples by Professor Siciliano and his group, so the author of your textbook, around the same time, probably a couple of years later than the video that I showed before. So when you have uncertainty on the environment geometry, then problems becomes more critical, and especially if you combine them with friction and compliance. However, at that stage, you can decide to use all the information that you collect while executing the task, so while controlling velocity along the tangent direction to the surface and force along the normal direction. I'm now thinking of a three-dimensional task in position without taking care of orientation, which is, as usual, a complication in terms of mathematics. But the principle is exactly the same. So instead of throwing away what is not consistent with the model, we can use this information to update online, in real time, the model itself. And this can be done by the internal sensor of the robot or by external sensor. For instance, if you have a vision, a camera that overlooks the scene, so it can recognize from the camera the geometry and so adapt by sensing. So without having a priori model, generate the model while the robot is moving on the surface. But for doing this, we have seen also in the introductory lecture on interaction with the environment that you can use force in order to do this estimation. And so let's consider now exactly this problem. So the question is, how difficult is to estimate an unknown profile of a surface on which the robot is in contact using the information that comes from the velocity and force measurement. Again, force measurement by a force torque sensor. Velocity, there's not a Cartesian velocity measurement, a direct one, but it's modulated by the Jacobian starting from the encoder measurement differentiated numerically. But this is a long story, I will not repeat it again, so assume that we have velocity and force measurement. So can we do something with this? Should we use velocity measurement? Well, if we expect that the velocity are tangent to the contact, if we measure velocity in the Cartesian space, we expect that that direction is the tangent to the surface. And similarly, if we use force measurement and we expect that forces are always normal to the surface, then by measuring those forces with a force torque sensor and doing the proper rotation and transformation, we expect that the normal direction, the direction of the measured force is in the normal direction. So we have two complementary information about the tangent and the normal to the given surface, which is unknown a priori. But what happened? In the normal direction, which is the nominal direction of the measured force, because of friction, what we sense, so the measured force, which is the violet vector here, is slightly rotated from the normal. So we are controlling Fn, but in fact we are measuring F in violet, and we have a tangential force which is proportional to a coefficient, this is a Coulomb friction, to the normal force that we are realizing. And in fact this coefficient mu can be given the form of a tangent of an angle, and the angle gamma is what is killing us in a sense. We would like the gamma should be 0, but in fact it's different from 0, and we have a tangential force in our measurement which is not consistent with the geometric model. So should we use the measurement F in violet to understand what is the normal to the surface? This would be wrong in this case, because the normal is in fact the red arrow. On the other hand, with the velocities, and we assume that the tangent direction is the nominal direction of the measured velocity, so the tangent of the surface should be there, but because of the associated compliance that we mentioned, what we actually compute, so from measurement, is a velocity, the v in violet, which is pointing inside the surface. Okay, so we have a small component along the actual normal to the surface, which is wrong. So we imagine that the tangent is along the violet v, but in fact it's along the blue one, which is the correct tangent. But we cannot use velocity information. So both type of measurement are affected by some physical phenomena that produces inconsistent data. So the idea is to use both methods in a mixing, to do what is called, has been called over the years, sensor fusion. And we do this by using a recursive least square. So essentially there could be many methods that can be applied. We estimated the tangent direction from position measurement using the recursive least square, so fitting data, let's say polynomial data of path on the position measurement and updating the coefficient properly. And once we have done this, we estimate also the friction angle gamma so that we can eliminate this effect. And we do this using both the current estimate of the tangent direction and the actual force measurement. In this way, we can use both sensors, fuse them in a suitable way, and update our model while we go on. Of course, once you have normal and tangent direction, you can use this as your task frame, and this will move and rotate accordingly to the progression of the task. There's an extra part, in fact, when we lose contact, or at the beginning where we are not in contact and we don't know where the environment is. Of course, you have some babbling operation, so you explore according to a logic where you expect to have a contact, so you move slowly in various directions until you get contact from the force measurement. From there on, you switch on your hybrid force velocity controller, or as we have seen, you may not need to switch this, because in the force control direction an impedance-based law can be applied also in free space. But indeed, when you choose the direction to exploration, this requires some exploratory logic. And the same happens if, in case you lose contact because you have a high curvature of your surface and you're proceeding with a high tangential speed. There could be a situation where you detach because you are not able to process data fast enough, especially if the contact is particularly stiff. So you have to recover contact again, and you use the same logic. You go back and then you look for the surface again with an exploration, a local exploration. So we have done some experiment first on an object, which I will show you later what was this object, but essentially this was an object with a circular surface, so with a given radius, that we needed to trace at constant speed while applying the force. So remember that this estimation is being performed in real time while we are already trying to achieve our hybrid task of force and motion control. So this is a purely position-based estimation of the tangent to the surface. You see that while time progresses on the x-axis there are samples at 1 millisecond probably, so there are many samples here. And you see that the tangent in degrees with respect to the horizontal goes from 100 degrees and then decreases until 0, so this is horizontal, and then changes to minus 100 degrees. And you see that there's a linear profile associated with the fact that the angle of the tangent is, when you trace the circle at constant speed, is changing linearly. Okay, and all the bouncing that you find are related to some uncertainties that are residual to the presence of compliance, to the presence of friction, and all the effect that we have seen before. There are extra peaks which are related to a specific nature of the object that we are in contact with. So this is the estimation based on the tangent. Is this correct? We don't know. We don't know really. I mean, we know the object, so this was an experiment, not a simulation, made knowing the object just to compare the result. Indeed, you could do the same using the force information from the force torque sensor. Indeed, you're estimating the normal and then by 90 degrees the tangent. So to compare the two graphs, here is what happens if you're using only force information. Now here the peaks of force from time to time are larger, and there's a clear explanation from this. So is this the correct one? Again, we don't know. If we compare the two measurements, so we put at the same instant what we have estimated using position-based information and velocity indeed, or force-based information based on the force torque sensor, we see that the difference may be large, of the order of 7, 8, 10 degrees, with some larger peaks, and this is exactly when the force has a peak behavior in measurement. So the two things are clearly different, and 7, 8 degrees on the average is quite a large error in orientation. So the idea is that probably better results could be obtained by doing sensor fusion. And in fact, here is the final result. The object, the mysterious object that I'm talking about, is in fact the contour of a film reel of a movie. The radius was 70 degrees. There are some tags, regular tags placed, let's say, every 45 degrees, more or less. And these are the situation where the force measured on the normal has a peak, because in fact it enters for a while, expecting instead having a perfectly circular surface to be reproduced, or estimating the circular surface and then having a sudden variation. Of course, if the curvature of the surface is large, the effect on estimation will be more sensitive. So the recursive squared, combining all the measurement and using data fusion from both the force and the position and velocity measurement, essentially dealt with the update of polynomial fitting, quadratic polynomial fitting locally to the surface, and updating the coefficients of this polynomial. In this way, from the polynomial and from the local fitting, which combine the information, as I said before, so estimation of a tangent and the correction of the angle due to the friction, to the Coulomb friction. From this functional polynomials that we have fitted, and we are fitting recursively while we move on, we can compute the tangent and the normal, and therefore regulate the force along the normal and the velocity along the tangent. This is a two-dimensional task, in fact, so we don't care about extra quantities. But this shows that you can do, and this is more or less exactly what we expected. So a radius of 17 centimeters and the shape, which is reminding quite closely the one of the film reel. and in fact also the small discontinuities at the center and 45 degrees before and after, which corresponds to these tags on the field reel. In fact, in the experiment, while identifying this surface, we have also kept the normal force equal to 20 Newton. So this is regulated with the simultaneous motion and estimation and regulation of force. So the motion at a constant speed. And you see again the peaks coming in correspondence to the discontinuity of the circular surface. So these are corresponding to the technical term are the grooves present on the film reel contour. So these discontinuities are detected. Now, with this in mind, we perform a more general contour estimation. In fact, we built in-house a wooden profile. It's funny because I found this wooden profile, which now is stored somewhere in the lab. I found a similar contour in another lab around the world. So we didn't know even the exact surface, we just manufactured this at home. And we used the MIMO CRF robot with the Hungarian 64-star sensor for this, which is again essentially a 2D task. So this is a roller coaster profile, montagne russe in Italiano, that we should follow. So we have to detect the tangent and the normal, and we do this while regulating the constant velocity along the current tangent and a constant force along the current estimated normal. Okay, so we do all the same estimation and hybrid control. And this is the result of our method. In fact, the first is an approach, so we are getting in contact, and then when we are in contact with stuff, you will see that there is some compliance in the finger here. There's not a nose, but in fact something similar. The friction at the contact is very large because we have a wooden to rubber contact, and you can imagine how large is the friction while sliding on the surface. And we are controlling both quantities, tangential velocity and normal force. Here you see in a peak, this is very critical. We lost contact many times there because the curvature was relatively high. Of course, if you move slower, then the chance to lose contact is much slower. If you go faster, then because of the sampling of quantities and the needs to update command, not faster than I think here was 10 milliseconds, then this could be dangerous. This is again the same task or a different run as seen from a different view, and again we use this recursive least square. At the end of this video, you will see also the reference paper if you're interested into it. It's a paper of 1992 by a member of the robotics lab at that time. The robotics lab was placed in San Pietro in Vincoli in Via Augustana, where a part of the garden was. It's 1993 in fact. Okay, so this is almost it. Another application of hybrid force velocity control is the one shown here. In fact, you have seen this picture before. Unfortunately, I don't have a video of this, which is an experiment conducted by a master student in a ABB research center near Rome, which no longer exists. Unfortunately, they moved it to Milan. But this is another hybrid force velocity control, but implemented in a poor man fashion on one side and in a more sophisticated on the other side. The poor man fashion is because the ABB here had a closed control architecture. So we could not modify, in fact, the behavior of the velocity of the end effector. But this system had a special device for, let's say, debarring, which consists of this rather heavy end effector mounted on the flange of this 6 degree of freedom ABB robot, which carries a blade which is pneumatically actuated. There's also an extra passive compliance in the tool at the end effector, and all this should be used to remove the excess of material, which is a special gluing element by polyvinyl butyral, so PVB, which when becomes cold, it's quite hard. And this excess of material, which is used to glue together several glass layers to make up a car windshield, the excess of this material it comes out of the border, of the nominal border of the contour. So this should be eliminated before mounting this car shield, this windshield on the car bodies. So in this case, the tangential velocity along the normal direction, the tangential direction to the nominal shape, which has very sharp edges, as you can see. So if we go down, stop, and then restart when we get to one of the corners, was assigned to the controller, to the robot controller. On the other hand, the control of the normal force was implemented with suitable force control scheme. So it's again a hybrid controller in which one part is devoted to the closed architecture robot controller, while the force direction is explicitly controlled. So the debarring tool contains, in fact, two blades for cutting the exceeding plastic material. The first one is actuated by the pneumatic actuator. The second is like the Gillette blades for cutting your bird, is passively pushed against the surface and follows the first one, so that you can remove the extra material that you may have cut with the first blade. In addition, we have a force sensing device here. It's just a 1D force sensing. It's called the load cell, in fact, because we only need to measure the force along the normal, and we don't expect inconsistency in this sense. And moreover, on the tools, there's a control system which, besides commanding the pneumatic actuator according to the load cell measurement and for regulating the forces, this comes from the technological process. We know how much force we should apply, not too much for not damaging the contour of the windshield, but not too little in order to avoid removing this extra material. So the value of the force should be regulated from technological aspect. So on board of the tool there's a control system, but it's important that this control system is also exchanging data with the ABB robot controller, so using a local area network or an Ethernet connection in general. So, and for this situation here, you can see a bit more detail. There was a thesis on that word. On top you see the physical system, so the robot carrying the base. On the base there's the pneumatic actuators, there's some passive spring connected to the support where the load cell is mounted and measures forces. And then there's a blade support. The blade itself is an elastic plate and is in contact with the uneven surface of the glass of the windshield. So this physical system corresponds to a very simple to a mathematical model which has linear dynamics. Is made by masses and springs in series. You see the position of the various elements, the x of the glass surface, which may have some disturbance on top. You can simulate this, for instance, before realizing an experiment. There's a stiffness of the blade, there's a stiffness of the load cell, in fact. There's a stiffness of the spring present between the pneumatic actuator and the load cell. And there are position of the various rigid bodies, including the robot, which may get closer or more distance to the surface. And if you have such type of system and you're trying to regulate force, so measure the difference, in this case, between the position x of the support of the blades, x sub b, and x of the support of the load cell, so the difference between these two variables would be multiplied by the stiffness of the load cell, would be the measured force which should be regulated. As you can see, you have some workpiece dynamics, which includes also the stiffness of the blade, and you have some dynamics before, which is the spring of this deburring tool. So you have multiple mass spring system, and we have seen that the presence or absence of extra compliance may damage the regulation loop. So here a PI controller was used for regulating forces, if I remember well. But the methods can be seen, at least proportional controller and their stability using linear models and root locus techniques was already presented in one slide, and you have an extra technical paper in the material in the course website. So let's conclude this lecture with looking at a few videos, which are video clips extracted from a longer full video that is available again in the course website. And these are experiments performed at the University of Naples, now it's called Naples Federico II, in 1994, using the Comau smart robot that they had in their lab. I think that this video, although historic by now, are very well illustrating the various control, at least some of the controllers that we have seen so far from a theoretical point of view. So let's look at this video. It's about 10 minutes as a whole, starting with the first one. First one is compliance control. Now remember that in compliance control, so you just modify the Cartesian stiffness of the robot, and you don't use a force torque sensor. In fact, from this figures from that illustrate this miniature that illustrate the videos, you can tell that under the hand of the researcher, which is grabbing the end effector of the robot in the compliance control scheme video, there's no force torque sensor. That metallic flange has no black object. The black object can be seen in the second and third and fourth, in fact, miniatures. So in the first case, there's no force torque sensor. In the other cases, there is one. So let's start looking at what happens with compliance control. So in this case, we can choose proportional gains at the Cartesian level, and we can have a stiff control, so with large proportional gains. So if we push, the robot will not move. And we can push in any direction if we have selected large stiffness gains in the various directions. Indeed, now if you use the same controller for tracking the path at a reasonable moderate speed, this is a circular path in the Cartesian space, actually in a vertical plane, using the same gain that you have seen in the previous part of the video, which are those that will resist to forces applied to from the external part. Now, if you reduce the proportional gain, the robot will behave in a more compliant way, so will accommodate and then return to the same initial position when you're pushing or pulling. And this can be made six-dimensional in a sense. Now, if with the same low gain you try to trace the same circular path as before with the same speed, you can immediately realize that you're not doing really a circle. You can tell it from this video, or you can see it directly on this VCR screen. I don't know if you've ever seen this before. It's like in our system. You see that there was a circular path. You can see it now. A circular path perfectly realized when using large stiffness gain in this compliance controller, and in fact you're doing a kind of an ellipse rather than a circular path when you're using low gains. Low gains, however, are associated to a more compliant behavior. So when you're adding a force to a sensor, then you can impose impedance control. And when you do impedance control, remember that you can modify completely the apparent inertia at the end effector, or use the natural inertia, and in that case you will not, at the Cartesian level of the robot, and in that case you will no longer need a measurement of force and torque. So in this case, the authors have modified also the inertia, so use the full impedance model scheme, and they need, of course, the force torque sensor. Now, I remind you that impedance control in the Cartesian space assign a desired mass spring damper behavior in all directions in a linear and decoupled way, and this is realized through a preliminary feedback linearization control. Now, you will see in this video now what is the behavior first in free space. You see that if you don't measure forces, nothing moves. Let me stop for a moment this file. So in what follows, so again, if you don't push beyond the force torque sensor, there will be no excitation force to the model. So the model is not feeling any contact force and is imposing a position, because there's no tracking here, with some gain that are related to the mass, stiffness, and damping. So it will essentially not move. But indeed, when you're pushing on the end effector, it will react with the given choice of parameters. Now, in the following part, you will see how this transient changes when you change parameters. So, for the first case, assume that the inertia parameters, so the mass and the damping parameters, have been chosen, and you see the behavior when you're having a small or a large stiffness gain. Large stiffness gain corresponds to small displacement, like in this case, while low gains, stiffness gain, correspond to the large displacement, given the same M and D and the same applied forces. Here you see that lower stiffness corresponds to larger motion. And then when you release, the robot will go back to the same position. Now you can also choose a stiffness and the mass, apparent mass, and change the damping. If you use large damping, you have a small overshoot, but if you use low damping, like in this case, you will see oscillation and overshoot with respect to the desired position. So you can see that those parameters play a very nice role. Now you can also use an anisotropic choice of parameter in the various Cartesian direction, so to be very stiff or very damp in some direction and differently in another direction. And finally, the robot is now executing a circular path, but this circular path is then prevented by the presence of a box. And when you're doing this path, what happens is that you execute exactly the path in free space, and the robot becomes compliant when interacting. And for instance, here you see that in this, let me stop this. In this VCR view, you can see the circular path. So the end effector is tracing the path in the free space. When it touches the box, which is rather compliance, it's a carton box, it will comply with the surface and not execute, move on the tangent on the surface itself, so making an error in terms of position. In order to have this behavior, we should be sufficiently compliant, but not too compliant in the choose of our model. So have a stiffness parameter which is not low. Otherwise, we would not trace correctly the circular path in free space. But if we are too stiff, then we will tend to enter the surface and apply large forces. And you see that the forces that arises in contact are shown in the second plot on the VCR. Okay. Now, the third video is in fact pure force control. Let me see what it is. So again, in these cases, the first part of the video will show something that we have seen before. So we push on the force torque sensor. If we push before the force torque sensor, the robot is position controlled and will not move because it doesn't sense any force. If we push instead beyond the force torque sensor and we set as regulating force a zero value, then the robot will follow the hand of the human that pulls or pushes the tip. So it's the joystick characteristic that we have seen before. So let us see this first experiment, and then we will comment on the following one. You see that as soon as you release, since there's no position reference but just zero force reference, when you're releasing contact, the robot stops in the position that has been reached. Otherwise, you move it like moving the joystick, pulling and pushing the robot from the nose. And a sense of direction, or let me stop here. The sense of mass that you see depends on the parameters that you have chosen in the force controller. Now, in Naples and also later on in different places, they have implemented this scheme together with an inner position control loop. What does it mean? That the robot is in fact position controlled at the Cartesian level or at the joint level. Now we imagine that this is made at the Cartesian level and the inversion is performed inside the scheme, so with the Jacobian inverse. Remember that this robot has an open control architecture, open CS3 or something like that. Is an open facilities made available by Comau for research purposes and beyond. So you can really modify the controller and enter at the current or torque level in these cases. So if you assume that inside there is a position control loop, so if you specify a position at the Cartesian level, the robot will reach that position. However, this reference position is not generated independently, but is the result of an external force loop. So if you specify a force loop, a desired force, for instance, inside, in the direction of the carton box, on the vertical direction, and you're not measuring any forces, so the force controller will generate a command of motion. And this command will be treated as a position reference by the inner position controller, and so you will try to reach this situation. Of course, when you're getting in contact, then the position controller will remain unattended because you cannot really penetrate the surface, but the external force loop has an integral term, so it will apply more and more force until it reaches the desired one. Okay, so this is what happens when you're having an internal position loop, which is driven by the output of an external force loop, which includes an integral term. And here we will see the continuation. So you get approach, and then you will push enough until you reach the desired position. Of course, when you reach this desired position, you release the controller, you move the robot away using force control. And here you see the resulting track. In free motion, you're getting straight on the vertical until you touch the environment, and at that time, your reference of force will get to the desired one. Instead, if the inner loop is a velocity loop, you can see it also from the approach phases that the end effector is drifting from the vertical. Okay, it's drifting from the vertical, and even at the contact, there's a mistake by this type of loop, which is not recovered. So you're going down in the free space along a diagonal path, which is not the right one. And again, when you're in contact, you're not realizing the desired force. There's a residual steady state force at the contact. And there's an extra normal tangential force, which should not be there. So in fact, the message here is that you should use an internal position loop if you're doing this cascaded control with the external force loop and an internal motion loop. This is not what I proposed before, but is an example, another example of the possibility that you have in this context. And finally, in Naples, they implemented a couple of years later than us also a hybrid force position controller on this Comau version, so an industrial arm, not the prototype that we have used. And in this case, again, you have a situation where in free space you're controlling separately a zero desired force on the horizontal plane, so the robot will follow the hand, but a very steep position control on the vertical, so that you will not be able to move the end effector up and down while you're free to move the end effector on the horizontal plane. And the same is achieved while in contact with the surface, so the tangential velocity is being controlled, the normal velocity is controlled to zero, and the orthogonal velocity on the plane is controlled to zero, and the normal force with an 80 sensor, as you can see here, is regulated to a desired value. And here you see that the straight path is perfectly traced, both geometrically and in time, so the speed along the path is being regulated, while the normal force is being regulated as well, using this hybrid control, and knowing everything about the environment. There's no estimation or identification in this case. So this concludes this part, and concludes also the standard part on control. As anticipated, we will treat with Professor Bunditelli visual servoing in the next lecture, and we will resume then with the final part of the program, which covers some seminarial type topics, essentially detecting failure of actuators and possibly of sensor in a robot, and the large chapter of human-robot interaction under safety premises, so collision detection, and under active collaboration. Thank you for listening.